For revision purposes, one of the section B questions is very likely to be something that requires you to analyse an AC network to find its frequency response and possibly its step response and the location of the poles and zeros. People seem to have a bit of trouble with this, so this is a short video just illustrating a few of the more common circuits and the techniques required. Probably the simplest circuit is this one. It's just a resistor and a capacitor. I'll call them R and C. Now the frequency response of this, usually called H omega or HJ omega, doesn't really matter, is V out over V in, and this is just a potential divider, so the standard potential divider formula can be used. In this case, V out would be this impedance here divided by the total impedance here multiplied by the input voltage there. So the ratio of V out to V in is just the impedance of this thing here, 1 over j omega c, divided by the total impedance in the divider, which is R plus 1 over j omega c. Now, we're trying to get this into the form of a polynomial divided by another polynomial, and we haven't got that because we've got terms in 1 over j of omega, and we want terms in 1, j omega squared, that sort of thing. So we need to do some algebraic manipulation on this. And in this case, fairly straightforward. If you ever see anything with a j omega on the bottom, then just multiply by j omega. In this case, I'll multiply by j omega c. We'll make the resultant expression a little bit easier. 3 terms here, all of them need to be multiplied by j omega c. That gives me a 1 on the top, a j omega c times r on the bottom, and a 1 on the bottom there. And I can rewrite that in this form, and we can see that we now have a polynomial on the top and a polynomial on the bottom. Compare that to the standard form, which is just the zeros on the top and the poles on the bottom of this form here, j omega divided by the pole frequencies. Well, on the top we've only got 1, so we have no zeros at all. On the pole side, the bottom, we do have 1 pole, and you can see, comparing this to this, that CR must be 1 over P. In other words, there is a pole at 1 over CR, and that's in radians per second. If I wanted the pole in hertz, I would have to divide that by 2 pi. Don't forget that, it's an easy way to lose marks. Pole frequency in hertz here is 1 over 2 pi RC. Plotting that on a Bode plot, you would just start off going constant at 0 dB. You can tell it 0 dB because when omega equals 0, this term here just becomes 1 over 1, which is 1. That means the output is equal to the input. That means the gain is 0 dB. So we'd just start off with 0 dB, and we would carry on until we get to the pole frequency, 1 over 2 pi RC in hertz. Can't quite see that, I'll move it up. RC in hertz, at which point it would change and go down by 20 dBs per decade in slope, and the actual frequency response would asymptote to both of those two things. It would look something like that, where it is 3 dB down at the pole frequency. That would be minus 3 dB. Right, that's about the simplest one. That's probably going to be simpler than any that you find in an exam. We'll do a slightly more complicated one of the kind of level that you might find in an exam in the next video.